Hello everyone, we'll begin our coverage of Chapter 2. In this video, we'll be dealing specifically with the population regression function. So as usual, when we begin this exploration of a new concept, we want to start with a definition. And this slide gives you a definition of the population regression function. And what I'd like to highlight here is that the population regression function gives us an expected value of some outcome variable y based on specific values of some control variable x. And specifically, we want to look at this relationship between x and y such that our estimated, or at least our parameters, model parameters, are linearly related to the outcome variable. So the model parameters in this case will be beta 1, which is an intercept parameter, and beta 2, which is a slope parameter. Another thing I'd like to highlight on this slide is that in the Appendix A work that we did previously, we were looking at characteristics of distributions. So we were dealing with parameters such as mu, which was the expected value, or sigma squared, which was the variance of a distribution, and we also looked at other parameters like skewness and kurtosis. In this case, we're looking at a model of data. So this we think of as a model, and as always, a model is a simplification of some reality. And in the case of linear regression, the reality of the relationship between two variables may look something like this. Whatever the y outcome variable is and whatever the input or control x variable is, these two may be related to each other like this. You might have some cloud of data points. Maybe it's upward sloping, maybe it's downward sloping, maybe there's no decipherable slope. But either way, what we are doing when we impose this linear regression model on this data is we are saying that we can describe this data by a straight line. Okay, imagine this was a straight line, this blue line. We can describe all of these individual data points. We can compress them onto this single line. And of course, when we have a single line, we use the familiar y equals mx plus c formula to describe any straight line in xy space. In this case, our beta 1 parameter corresponds to the constant, and our beta 2 parameter corresponds to the slope. Another way to phrase this is to say that a regression model involves data reduction. It compresses a cloud of data points onto a single line. Now, because we are dealing with a model, we will have deviations from that line that we observe in reality. All our data points will not lie on the regression line. Another important aspect of the regression model is that it comprises a deterministic component as well as a stochastic component. So you might recall from Chapter 1 that we described the model without this u term as a deterministic model. And then we describe the model that includes the u term, the statistical or econometric model. And that is because we know that there's uncertainty, necessarily there's uncertainty in our model. Not all of the data points are going to lie on our regression function, on our line through the cloud of data points. So in your textbook, you are given an example where you have 60 families, and this is considered the total population for these data. You have 60 families with a weekly income X and weekly consumption expenditure Y. Now in economic theory, consumption expenditure will be related to weekly income in some way. So usually we would say there's a positive relationship between income and expenditure. And we might imagine that a linear relationship between these two things will be a good description of the relationship between income and expenditure. So on this slide, we've estimated a regression function. So this line over here is essentially given by beta 1 plus beta 2 x. And again, this is the expected value of income based on specific values for consumption, the expected value of consumption expenditure, y, based on specific values for weekly income, x. And this graph highlights the distinction between the deterministic component of a regression model and the stochastic component. So if we look at x equals 80, which is the first value on this horizontal axis, we notice that the expected value of y, given that x equals 80, is given by this big dot over here that lies right on the regression function, right on that line. And that is the deterministic component of the model. However, there are also other values for y at the same x value. So the one right at the bottom here is 55, for instance. And there's another value just above that at 65. And then there are a couple of values also above the regression line. And you can think of this as the stochastic component of the model. And to find the values of that stochastic component for a given x value, we take the observed y values and subtract from it what our model tells us that y value should be. So going back to the previous slide, for x equals 80, we observed that there was some y value. So although the predicted value, the expected value of y, given that x equals 80, is given by 65, we observed in one instance a y value of 55. And if we take 55 minus 65, we get an error term of minus 10. And you can apply that calculation for each x value and all of the different y values that we observe. And when you do that, you will arrive at some distribution around the expected values. And what the regression model does is minimize the deviations between the expected values and the observed values for all x and all y. But we'll get into that in chapter 3. Now, as we've seen, when we impose a regression function on some set of data of two variables, we have these error terms. So why do we have these error terms? The short answer is that we are dealing with a model. And in general, a model does not equal reality. We are using a model to try and give us some sort of description of reality, but no model is ever going to give you a precise description of reality. And that's the short answer. Now we can dig a bit deeper and ask, why is that? Well, models usually are derived from some sort of theory. Some people might even say that a model is also a theory. But we can also distinguish between those two things. Either way, errors can arise due to vagueness of theory. In our regression model that tries to explain the relationship between income and expenditure, there might be several other things that also explain consumption expenditure among households, other than weekly income. And if that is the case, it necessarily implies that our model is, or our theory is, quite vague. Unavailability of data is another problem. Let's say that we discover that average age of members of the household is also an important variable that explains consumption expenditure. and that older households tend to spend less than younger households, for argument's sake. But let's say that we don't have those data. We don't know what the average age of all the households are. So we just leave it out of the model. And if that is the case, again, our model will be wrong, and that error will show up in the U terms of the model, the error terms. Now, following on from the previous argument, which is that there may be other variables that we can think of should go into a model, but that we might not have data for. Let's say that we do have data for all variables. Well, it might be the case that there are an innumerable number of variables that might explain some phenomena. So we might think of any number of variables that might be important for explaining household consumption expenditure other than income. Things like education levels, things like religious values, things like geographic location. All sorts of variables can be thrown into this model that we might believe has at least some relevance for explaining expenditure. But we might be prudent and say that we're only going to keep the core variables, the most important variables we believe to explain expenditure, and we're going to leave out some of the more peripheral values. Let's say we believe religion does matter, how religious someone is might explain how much they spend, but we're going to leave that out because we don't believe that it's that important and explanatory variable. Again, when we do this, we will be introducing some sort of error into the framework. Then there's also just basic intrinsic randomness of human behavior, and this is what makes the social sciences such a hard discipline, which is that we just don't understand human behavior in a precise way, certainly not in the way that we understand things like physical phenomena or even biological phenomena. So looking at the expenditure income model, some households might just adopt a minimalist lifestyle. So they might have very high incomes but spend very little money. And that's something that's very hard to capture in a model. Another factor that could result in model errors are poor proxy variables. A proxy variable is a variable that you substitute for some other variable. So for instance, if we don't have a variable on income, or at least we don't have the actual values of these households' incomes, we might substitute it with a variable of self-reported income. So we can go out to these 60 households and go ask them, how much do you earn? In many cases, perhaps even most or all cases, we won't get the exact number since people are somewhat reluctant to divulge their incomes. So this might be a poor proxy for income in this case. Then there's also the principle of parsimony, which merely states that we should try and keep our model as simple as possible. And there's various reasons why we would want to do that. It's not appropriate to go into all of them now, but in general, for statistical analysis, we should apply Einstein's dictum that a model should be as simple as possible, but not too simple. And then finally, it's possible to adopt the wrong functional form of a model. So we might have the right variables in our model, but we may not be specifying them correctly. So perhaps a linear relationship between x and y is not quite appropriate to explain the relationship between two variables. And that brings us to the end of this video. In the next one, we'll be looking at the sample regression function. Thank you.